Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you're watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on the YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream. All right. Hello and welcome everybody.
Is it spooky?
It is in the lower left-hand corner.
Oh, our name is spooky.
Our names are spooky, and hopefully I think questions will also come in spooky.
Oh, it's going to be spooky. We picked the spooky design because
Halloween
is next week. It's one week away. Is it Friday? It is.
It is Friday.
So actually next week is Halloween, but we're preempting Halloween with our own spooky design.
I was like, yeah, let's give this a shot.
Yeah, our names look like they're dripping.
Yes, yeah. There are the designs. Hopefully, we'll see when the questions come, and if those are also spookified.
Well, we have one, and let's not even wait. Let's just see what this looks like. Are we ready?
All right.
Let's see how spooky this is. Oh, it's so spooky you can barely read it.
Yeah.
Oh, that's amazing. I'm not sure if I like this. I can't even read it.
But it makes the questions much more terrifying.
It does. All right. Well, let's go with it for now.
Yeah.
Because I can read, on the chat, which is in regular text, not drippy, creepy text. But we're gonna go with this. It's Halloween time.
There's another one here. Well, no, Bangers is not. Creepster is definitely. I'm looking at the design.
Does it change?
It does. It does change. So I can change.
Do I have to undo it and then we put it back?
Let's see. Does it?
Hang on.
Did that
go? Oh, it did change. It's just italicized.
Now it's italicized.
This doesn't look creepy. It just looks italicized.
Yes.
That's creepy.
That's creepy.
Okay. It reminds me of. Do you remember that show? Are You Afraid of the Dark?
Yes, I do remember that show.
Was that a book too, or was it? No, that was just a show.
I think it was just.
No, that was that show. Yeah, it was a TV show, and that show scared the pants off of me when I was little.
Yeah, that's why I never watched it. All I did was just watch regular cartoons.
You know what it is? It's like there's a morbid curiosity about creepy things. And I really don't like horror movies. I don't like bloody things. I don't like slasher movies. It's not my thing. But sometimes it's like. You're like, I kind of want to. It's like, you know what I mean. It's like when you're driving and there's an auto crash on the other side of the highway, and you're like, oh, I better brake and make sure I see what's happening, as though it has any effect on you at all. Yeah, And I always find that annoying when I'm waiting in traffic for something that happened on the other side of the highway. But that's what creepy things are like, and that's what that show was like, and that's why I'm still having nightmares in my late 30s.
Yes.
But that's a me problem. So let's get to Azam's question.
So
Azam says, why does the capacitance retention percent increase to 120% after the addition of RGO, graphene oxide, in alpha Fe2O3 nanoparticles, whereas in pristine alpha Fe2O3 it is 100%? Please explain. Okay, so the first possibility is that you're calculating your retention percent wrong. The capacitance. Okay.
I wonder if we have an equation.
Well, I'm just trying to think out loud. So in some sense, if you're calculating your capacitance as like farads per, centimeter squared or per gram. So there's some follow-up questions that I would have. For instance, are you calculating your capacitance or as a specific to mass, to volume, to surface area, things like that, right? Because one of the things that might happen, for instance, is that, like, let's say you have, like, I'll just use round numbers here, and I don't even know that. I assume this is like a supercapacitor, so I'm making a lot of assumptions. But like, let's say you have 1 gram of Fe2O3, right? And it has a specific capacitance of some amount of farads or whatever. Okay, so you get like 10 farads per gram, right? And then after some time, the retention is like, how good did it do compared to the beginning, or something of that nature, right? And it's like you get the same number, so that's 100% retention. Like, it's the same number as it was at the beginning. It's almost like, it's like with a battery, the analogous situation is charge discharge. So the charge capacity is the same as the discharge. Now, the point I'm making here is that there's ways you could do this, right? Maybe you have the same 1 gram of Fe2O3 and you add, half a gram of RGO. Okay. Well, now you have 1.5 grams. And so the capacitance that you get will be different. You have more material there. You have more mass, more surface area, more volume, all of those metrics. And so if you're assuming to normalize, let's just say, by the 1 gram only, you're going to get like artificially boosted results, right? Like you're getting extra capacity from this graphene oxide. Now, maybe you're adding the graphene oxide. And this is again, batteries are kind of my easy, reference point here. But for instance, if you add graphite or graphene or whatever, often for a anode or a cathode, a capacitor, a lot of times you're doing so to impart conductivity. That's what graphene's really good at. And a lot of transition metal oxides, for instance, are not that conductive. So you add graphene to help the conductivity and then it performs a little better. But what also happens, again, for batteries, probably to a certain extent with capacitors as well, is that the graphene itself contributes to some of the performance. So for instance, in a battery, again, the solid electrolyte interface will be impacted by the amount of carbon you have. There can be secondary storage that can occur within the carbon. There could be primary storage that occurs within the carbon. And so the amount of coulombs or farads or whatever the unit is, in this case, that you get will be impacted by the amount of carbon you have. So if you're not accounting for that addition of your performance because of the carbon itself, you're going to draw the wrong conclusion that your material is acting better than it is, right? It's like I have iron oxide, it gives me whatever. Then I have iron oxide plus graphene, it gives me something better. But it's like it's not. The iron oxide is giving you the same, let's just say, right? All things being equal. But the graphite's adding a little bit extra performance to you. But now it's making you think that I have like better retention or better value or something of that nature. So that's my first kind of general thought, without knowing the exact values, of course, and how you're normalizing or not normalizing, things like that, is that if you're adding graphene or graphite or whatever, I'm guessing you're doing so to impart conductivity. And you just need to be careful that you're not missing the added, benefit or bonus in some sense that it's giving to your capacitance or your capacity or whatever, because carbon will do that, right? So I'm guessing, in my opinion, that most probably that accounts for your, whatever, 120%, like impossible retention, right? It's like, well, how can it be more than 100%, right? It doesn't even like scientifically make any sense. I think it's just a calculation error, and perhaps not accounting for that added material. That's my guess.
Yeah. No, I agree. No, I don't think I have anything to add.
Okay.
Okay. Yeah. So, but Azam, if you have any other questions,
follow up, Azam, if I misunderstood something, or my, or you say, well, actually, I did account for this way, and I'm still not sure. Yeah, please follow up and let us know. But that's my best guess.
Yes.
I'm not sure this next question is. I don't know what to do with it.
Tell me, organic chemistry reaction.
Yeah, Friedel-Crafts reaction.
Yeah, or Diels-Alder.
Ah, that's a good one.
Yeah, that one. I'll draw closer because Raghav, Raghav is asking, tell me an organic reaction. Well, I remember this one from college. Yeah, I think it was. I always thought it was interesting. It was like
I'm pretty sure I learned this one as well.
I think it's this and something like this.
There's a lot of lines.
Yeah, this goes here, and then this goes here, and then you get and then you get cyclohexane. Some organic chemist is really unhappy.
Some
with
organic
me right
chemist
now.
is just raging at their computer.
I know. Very unhappy. But I know that this is a reaction.
Something like that.
There's some, yeah, because it was just like, yeah, the double bonds just they literally just move here in a dance. That was the thing they described.
It's a dance.
It was a dance. It's like, that's got to move here, that's got to move here, that's got to move here.
That's
and
tremendous.
then boom, you have that. And then so people thought, oh, if I functionalize these, I can get.
You got to draw the circle inside the cyclohexane, right? Isn't it?
No, well, if it's cyclohexane, it doesn't have a circle.
Oh, there's no double bonds?
I don't think so. Each one of these double bonds.
Oh, it's not
became
benzene
a single
ring. It's
bond.
cyclohexane. It's
Unless
it's not benzene ring.
Oh no, wait, you're right. I think this goes there. Yes.
Oh, there's one double bond.
There's one double bond because this double bond goes here. This bond goes here.
But one double bond.
One double bond. Yeah, there we go. Yeah.
I hate organic chemistry.
Yeah. That's why we're not.
That's why we're electrochemists.
Yes.
Because this stuff, and the funny thing, I think I mentioned Friedel-Crafts reaction because I honestly think that the only thing, which it probably says a lot about me in a bad way. The only thing I remember from my one semester of organic chemistry in undergraduate is Friedel-Crafts. I don't even know what it is. I just remember
the name.
I remember that as a name of a reaction. And I remember thinking back then, which was 950 years ago, before the invention of computers and the internet, that why do I have to memorize this for a quiz? I'm just going to look this up later. I thought that back then. You kids these days, you don't even get it. We didn't have the internet the way you have the internet. And I still remember thinking, like, why would I memorize this reaction? I can just look it up later. Even then, So
I did get it right. Okay. I looked at the Diels all direction. I'm like, okay, yeah, I did have to put the bond on the other side.
Well,
but there is no circle in the middle.
No, you have the one double bond, but you drew it correctly.
And I drew.
So you need to retract your frowny face.
My frowny face.
Yes,
I did get that right.
It should be a happy face.
That should be a happy face.
I hope that is the best organic reaction that you've ever seen, Raghav.
That's my hope. Yeah, most beautiful. The dance.
That's
the
right.
Electrons have to move in this.
I will not be contributing to this because I am terrible at organic chemistry. Instead, we will move on to Yogesh's question.
Yes.
Joining us on LinkedIn. Oh, it's still creepy.
We can change it if it's too too difficult.
We're committed at this point. It's been like 15 minutes. We're going with it. I can't read any of that. I can only read the comment on our program on the right. So if it appears that I'm reading this drippy text, that is incorrect. I can't read it. In any case, Yogesh says, warm greetings. Currently, I am a PhD scholar exploring SWASV for paraquat pesticides detection in 0.1 molar PBS solution at pH 7. I'm not sure what SWAS is. What is it?
I think it's square wave anodic stripping voltammetry. That's what I think it is. If I had to guess.
That seems to track because we just call it SWV. So the anodic stripping AS is in there, and that's probably right.
I think and
square wave anodic stripping that makes sense.
So that's what I think. But
for detection of something like pesticides, that makes sense. Right? Like you do like lead detection, you do like contaminant detection. Usually you have square wave as a means to analytically exactly, and then you strip it away or whatever, so you can do it. Anyway, my problem is if I repeat the recording data again, it's not completely overlapped. I mean the square wave curves.
And if it is stripping whatever the paraquat or the pesticide, then you won't get the same result. There's also, I would say, this is probably one of the hardest things in any kind of biosensor chemistry, is that the exact reproducibility from like sensor to sensor, experiment to experiment, always seems to change quite a bit. And so reproducibility is always very important. It's super hard. And so I'm not surprised that you don't get something that completely overlaps. Even if you do 2 cyclic voltammograms of a very well, reproducible system, it's hard to get them to overlap exactly on top of each other.
Yeah.
Now, if it's a little bit, because it's square wave, then I think that's okay. I would pay attention to the y-axis. Oftentimes, as people we're prone to looking at shapes. It's like, oh, we look at the shape of something. It's like, oh, the shape of the first square wave anodic stripping voltammogram is wrong,
or is one thing, and then, oh, the shape is, it looks so super different, but it turns out like, oh, it's only like 5 nanoamps difference, and you're looking at something that's on the milliamp scale, or you're at the limit of detection for what you're looking at. So to a degree, I'd pay attention to that, and then for sensor research, look at the deviation of like peak anodic current with different amounts of the paraquat, because that's what's going to give you the analytical information. Some of the other aspects of the shape, they can change a little bit, but it's not too surprising that they don't overlap completely.
I'd also add, just as a possibility, I guess I'd say, that it depends on what your working electrode is, because it is sometimes the case in certain situations that the working electrode degrades as you do this, right? So it's like you do it once, then you do it again. And so let's just say you did it twice within like 90 seconds of each other, and it doesn't look the same. Well, it could be that your electrochemical signals, impacted your working electrode surface itself as well. So it's like, it's not the same, because the working electrode, while you think it's the same, like the same, I started at this potential, I went to that potential, I did this square wave pulses and whatever. Actually, it's like, well, after you did it the first time, you plated or detected this stuff and then stripped it away. But you actually did something as well to the working electrode, like maybe if it's like graphite or something, and it, slightly adjusted the oxide state on the graphite electrode, or the stripping actually stripped more that was there to begin with. Like there's a lot of other things that you probably would not know or like even consider are happening, but are. And then it makes, I'm not saying it's like an impossible thing, right? But it's just it's the nature of electrochemistry, because it's such a heavily sensitive surface science, right? Anything you do while you're thinking only of the analyte, you're thinking of just the pesticide, and all of that stuff. It's like, well, you have an electrode surface too, and if anything happens to the electrode surface throughout your experiment, because of the potentials that you're applying and the currents that are flowing, the surface might be changed ever so slightly as well. So like you might have to do some activation step in between. I'm just making this up on the spot, but like maybe you need to do like a restorative cleaning CV or something, in between tests, to like as best as possible, like restore my working electrode to some state. Like that could be something that's going on as well.
Because he hasn't actually identified what the working electrode material is,
exactly,
or the electrochemical, only the electrolyte, which is normal, like,
right? Exactly.
Molar PBS. There's nothing
but to that,
crazy about it.
Again, to that point, it's like people do these with screen printed electrodes sometimes, and sometimes the screen printed electrodes are like somewhat disposable, and so like if you're doing this for a while, you have to be careful, because sometimes you need to like, oh, I should get a new electrode at some point, because like I've started to deactivate my electrode, like if it's something like that. Now if you're working with like a disc or a metal sheet, like it probably ought to last a little longer. Like there's different varieties of working electrode, and in terms of their like longevity, perhaps, right? So some of those things could be at play. You just want to kind of double check that the condition of your working electrode is still as whatever you'd say, pristine, intact, or whatever, over time. Something like that. That's another thing that gets overlooked, I think, a lot. You just sort of assume your working electrode's great, everything's the same. Why do my results look different? And it's always somewhat the answer. It's like, well, you think it's the same, but it isn't. There's something that's not the same, right?
Yeah.
Welcome to electrochemistry.
Yeah, I remember someone asked you like an EIS question along those lines, like, "Hey, my impedance is super different, but I didn't change the system." And it's like,
you did.
You did. There's no way the impedance can be.
I know it's because a lot of times I just can wax on poetic about this forever, but it's like that tends to be a large part of our job. I mean, with what you said, it certainly happens with impedance specifically, but I mean, even in general, these kinds of things happen. And like, sometimes it's obvious. Like sometimes I'm always like happy in some sense when like, we're helping someone troubleshoot, whether it's on this live stream or it's just with our job, like, through email or through phone call or something like that. And a customer's like, well, why are my results looking whatever? And it's like, oh, because your counter electrode was, like there wasn't any solution in the fritted tube or something. Like it'd be an obvious answer, and it's like, oh, good. Like I feel, I don't have to go down the rabbit hole of like obscure possibilities, right? And then it's those are always the toughest questions, actually. Like for me personally, when it's like they're presenting, for example, their data, and it does look different, right? But all signs point to like all the other things were done properly. Like the reference electrode's there, the counter electrode's there, like their electrodes are fine, the solution is fine, and I'm like, oh man, what could it be? Like you rack your brain, and we do that all the time. And so sometimes it's like, that has to be my answer because I don't know. All I know is that it isn't the same. Something is different. Now, precisely what that is always really hard to answer, but that is just the reality. And it's one of the most frustrating things I can tell you as an electrochemist. You'll discover as you do this more and more that reproducibility is such a pain unless you're using a resistor and a capacitor, like, like actual solid state physics, components on your lab bench or your dummy cell or whatever.
Yeah. Yeah, no, definitely.
It's just the reality of it.
Just the mess of it all.
Mm-hmm.
So we have a question.
Daniell cell, Daniell.
Yeah.
I never know how to pronounce it. I feel like it's Daniell cell.
Yeah.
I feel like I've heard people say it that way.
Yeah.
Doesn't it have like 2 L's in it or something?
Yes, it does normally have 2 L's at the end.
I don't care how you spell. I'm not trying to comment on your spelling. Okay. This person, you know what I mean? Daniell cell, Daniell. It's one of those things where like in English, I always want to say Daniel, and I think it's Daniell because it's named after some person, right? I guess.
Yeah. Actually, I'm looking. It's a British chemist back in the 1800s, so it could have been pronounced any way.
Yeah. Who knows? Yeah. It's elusive. Anyway.
Yeah. I'm looking at Daniell or Daniell cells.
Is it zinc copper? Is that what it is?
Yeah, it's actually just zinc copper electrodes immersed in
cool. I know
copper
this one.
sulfate and zinc sulfate solutions.
I'll try it. I know this one.
And that's
for some reason it wasn't. Anyway,
it always sounds like it's something more.
Well, the thing is, I learned this like probably an undergraduate, and I feel like I didn't learn the name.
Yeah.
Like I learned this sort of typical it's not electrolytic because it's spontaneous. This cell, but I didn't learn the name. Maybe I did, and I'm just forgetting. It's very possible because it's considering I remembered nothing from my organic chemistry days. It would track that I remembered nothing because I'm not good at this. Okay, let's try the Daniell cell. So the Daniell cell involves 2 solutions. Usually they're separated in some way. Usually it's like separate beakers sitting next to each other. One of them will have copper sulfate. And help me out. Is it Zn2SO4? Zinc has isn't it? Zinc is 2+. So
zinc is 2+.
So it's
and copper is 2+.
Right. So they're both
yeah.
Just this. Okay. Yeah. I was making sure I didn't screw up the charges. So you have copper sulfate in one, you have zinc sulfate in the other. I should use different colors, but whatever, I don't care. In one side, we put a copper rod. So this will be copper. And on the other side, in the zinc solution, we put, any guesses? Zinc. Yeah. Okay. Easy. All right. I'm going to screw this up. What's the potentials of each? Can you help me?
Zinc solid to zinc 2+. Or do you want it in the form of a reduction?
A reduction, yeah.
So if it's in the form of a
zinc
reduction,
zinc 2+ plus 2 electrons. What is it?
To zinc would be positive 0.762 volts.
76. Okay.
Yeah.
So positive 0.7. So E0 is equal to 0.76. Okay. So this is zinc solid. And what's copper?
And copper for the reduction, copper 2+ plus 2 electrons to copper is plus 0.34 volts.
Plus 0.34 volts. I should put the unit volts. E0. Wait, they're both positive?
They are both. Well, hold on.
Is one of them negative? One of them should be negative. Isn't the copper one negative?
So if it's zinc solid to zinc 2+ plus 2 electrons, then it's negative. So and then you have and it's like anode. What is it?
It's cathode minus anode.
Cathode minus anode.
The zinc is the anode, right?
Yeah, the zinc is the anode.
All right, so it's
then
it's
you have
negative.
yeah,
The zinc,
so it's
the zinc is
minus
negative.
Yeah.
It's the value doesn't change. It's still negative.
Yeah.
I like to write it. Yeah. So okay. So the zinc one's negative. So the total reaction. This is the total reaction. This is the cathode.
Mhm.
This is the anode. Right. So it's cathode minus anode.
Yeah.
Total reaction is going to be it's cathode minus anode. So the zinc reaction would be written the other way. I just like to write it as reductions.
Yeah.
But you're right. It's basically it's the other direction. So we'd have Cu 2 plus. The electrons are going to cancel. Plus zinc solid goes to copper solid plus zinc 2 plus. So in other words, what we're actually doing is we're plating copper and we're ionizing zinc, right? So zinc is coming off this metal to form ions. Copper is plating on to make solid. That's the order of things that are happening. Right?
Yeah.
Do I have it backwards?
Well, no, you have it right. The only thing I would say is you should put the salt bridge in the.
No, I haven't done that yet. I haven't got there.
Yeah, you haven't gotten to
No, I haven't got there. I know there's a salt bridge. Yes,
you know there's a salt
for sure.
bridge.
Yeah, I haven't finished connecting it. Give me a sec. I got it.
Okay.
Right. So those are the reactions that are happening. Now, as Alex pointed out, I'm missing several things, right? These aren't going to happen on their own.
Yeah.
These have to happen in conjunction with each other. And they happen because, again, there's a spontaneity to this. You can see that if I subtract this, I get 1.1. 0.34 minus a negative 0.76 gives me, was it 1.1?
Yeah, 1.1.
Is my math good? Okay, got it. It's 1.1. So the voltage of the cell is 1.1 volts, which is 0.34 minus a negative 0.76.
Mm-hmm.
But how do I get that? Well, I have to connect these. I don't know, volt. I just put V, whatever you want to put it. So if I connect these, I can get the voltage between them and I'll get 1.1. But of course, what that means is that I'm going to have this reduction reaction happening down here on the copper and the oxidation happening on the zinc, but I'm not going to have any charge balance. So this won't happen like this. It wants to happen, but it can't because of what I have is electrons are going to want to move in this direction, right? From the zinc to the copper, right? This is getting oxidized. So these electrons on the zinc reaction are getting generated and released, and they're going to go towards the copper side here, right? That's where they're coming from. So the copper can plate, but that would mean that I have a buildup of negative going from right to left. It won't balance. I have to have a balance of charge. So what I do is I take a paper towel and I just bridge it between here. This is called a salt bridge. Now, this is a silly way we do it, sort of, it works actually quite nicely. In real electrochemistry, of course, we use more elegant kinds of cell designs, but really all we need is some way for a counterbalancing charge to happen, which means I need either negative charge to move from this solution in the other direction, or I need positive charge to move from in the same direction. So they have a balance of charge. And what is going to make that happen? Well, you could think about this as a positive charge. Zinc ions could go from right to left because I have Zn2 plus in solution. I also have SO4 minuses, 2 minuses in solution. I have SO4 2 minuses in here as well, right? And I have copper 2 pluses. I have ions. So that's the answer, is that I have charge balance via ions. And so we probably would consider the most likely situation is that the sulfate ions are going to move. I think I actually don't know 100%. I think it's possible that copper or zinc could also move and contribute. You could have some contamination of whatever, but I think the sulfate is what we consider mostly that moves.
I think so. I actually don't know.
Yeah, it's possible. I'm just saying we need plus to go from right to left as one possibility. So it's possible you could get like zinc into this over time. I think it's feasible. But basically, if we have SO4s 2 minus, that can like can travel across this bridge and go from one solution to the other. Now we have a happy, I'm going to draw a happy face, unlike your organic chemistry.
That's right.
Now it's happy and we have charge balance. We have 1 volt that we can read. We're producing zinc ions. This rod will eventually, over a long period of time, become less of a rod. We start dissolving all our zinc basically away. Yeah. And this copper rod becomes a behemoth of copper.
Yeah.
because I'm plating copper onto it. I'm being a little silly, but that's actually what's happening. I'm actually making the copper rod bigger and I'm making the zinc rod smaller. And this is a galvanic reaction, we say, which is being spontaneous. We don't have to apply any energy to make this happen. It happens naturally because of thermodynamics of these reactions. That's the Daniell cell. That is how it works.
All right. Okay. So that's good. So we got through that. Next question is from Alex Jeffen. Alex is asking, hi, could you please explain Tafel slope and how to accurately select data while plotting log of J versus over potential for OER and HER reactions? Thanks. Well, I guess
I have some data.
you have some data stuff about that.
Even
Yeah,
though
because
this
you,
is like my trigger point here.
I
do have
know.
some
I know.
data.
This is
let me pull up a thing.
Sure. Yeah. So we'll get to this.
So my my usual caveats, I'll try not to fly off the handle too badly, but my usual caveats here are as follows. Be careful with what you are making a Tafel plot from, because Tafel plots and the Tafel equation itself is specifically derivative from the Butler-Volmer equation, which describes kinetic current only. I need to get my plots here. I'm thinking while I do this log of IK.
Yeah.
Okay. I have some data. I'm going to put it into our software, and I just need to get the columns I need. So back to my point, right? You need kinetic information, right? Not every LSV or CV is kinetic information. So part of my answer to you, unfortunately, might be don't make a Tafel plot. And if you do, and you're wondering why you are struggling to find the right region, it's because your data is not kinetic and you shouldn't be making a Tafel plot to begin with. So that aside, let's say you do have good recourse to make a Tafel plot, and you are pretty confident that it's actual kinetic data. There's no convoluting factors. There's no capacitance. There's no double layer. There's no anything besides your Faradaic reactions with kinetic contributions to your current, and you're very happy about that. And that paper, paper had a good bit of information.
Yeah, I'm going to.
I'm forgetting what the specifics in that paper were. What was
the main? I think the main point about the paper, which I'll
yeah, no, please remind me, because now I'm bugging. It's bugging me.
The main point of this paper, and I guess I'll just share this very quickly while you get your stuff out. There's this paper, and I'm gonna get the DOI and then link it in the YouTube video. But it's ACS Energy Letters. Tafel slope plot is a tool to analyze electrocatalytic reactions. I hope that you read it. Mark Cooper's is very good, and this came out recently, just last year. And the idea behind this is that you actually plot the Tafel slope. Here we go. So I'm going to zoom in just a little bit. So A and B.
Changing it's bad, something like that.
Yeah. Oops. So
I think I have this paper. I need to check if I have this paper.
Yeah. So the note here is that the y-axis is Tafel slope, and you're looking at the change in the Tafel slope for every 10 millivolts or something like that.
Yes.
And if you notice that, the Tafel slope within a certain current is the same, or the Tafel slope is the same across a specific voltage range, then you know that it's a good way of gaining useful information, because if you're doing HER or OER, there may only be a useful range, and in this case he's got about 30 millivolts per decade, so that's 4 electron, because let's see, 360 is 4, so that's about a 4 electron transfer.
This might be ORR, I don't know.
Yeah, this could be an ORR example, but it's this Tafel slope corresponds to something normal, but in this range, there's all this other stuff that's happening that's convoluting your results. Only within this potential range are you getting the 4 electron transfer process, and so that's a helpful thing to do when doing Tafel analysis, is plotting the Tafel slope versus current density versus potential. I'm gonna get the link. I'm gonna stop sharing.
And
so
to that
you
point,
can...
what I'll do is show you, for instance, actively on what you might have for a Tafel plot. Forget about, I just imported this into our software here. I didn't even label the axes because I'm a good scientist. This is voltage or potential on the y-axis and log of kinetic current on the x-axis. So apologies for the mislead. I just loaded it in quickly and I didn't bother. But the point is, to that exact point in the paper, right? Your question could be interpreted a couple ways. How do I select the data? Well, on the one hand, you might say, well, if I have my LSV, what data do I select for my LSV? On the other hand, I can't even believe I'm going to say this. It's like the thing I rail about the most is that you can just make a Tafel plot of your data and then use that logic that Alex just shared with the Coper paper there to try to almost like after the fact inform which data you should select. So what I mean is this. So let's say this was an LSV. This was an LSV that I turned into a Tafel plot, right? Which means that I have I versus V. So I flip the axes, right? Down here is now, up here is now V or E, whatever. This is voltage, potential. I keep saying voltage because I'm a battery person. Apologies.
All's good.
I know. Well, as soon as a battery person, they'll feel me. That's what battery people say. But potential's up here. So I flip the axes and then I take the log of base 10 of the current. So I just turn my LSV into that. So it's like, okay, well, where's my data relevant or whatever? Well, to a certain extent, let's take the best case scenario. And let's say I know I have a 1 electron transfer process, which means that based on my knowledge of the Tafel slope, I should have 120 millivolts per decade, right? So one of the things that you could do, for instance, to your point, where's the data that I should select? And to the point of the paper, which is that like over certain potential ranges, I said it right that time, over certain potential ranges, I have no change in my slope. And it's, in that case, it was 30 millivolts per decade because that's a 4 electron process or whatever. Now in this case, let's say 120 is my number. So let's see the slope here. This is minus 14. So when this is minus 0.12, that's 120 because it's in volts, not millivolts. So if I adjust this, let's just say I can get this close to 120 right there, 118.
Actually, 118 is exact.
It is
right?
technically 118. I know. We say 120, but it's actually 118.
Yeah.
In any case, this would be like the first way for me to answer that question to a let's just say less theoretical, although it's theoretical because 120 is a theoretical number. That means something, but it's more of a practical, empirical kind of way to do this, right? So I'm saying here I have my slope that I am hoping to get, expecting to get. Well, what does this correspond to, right? I could just read the y-axis potentials here. So in this case, to that point to the paper, it was like, what are my Tafel slope? I don't know if he had like 1.46, 1.4.
Yeah.
I don't know if that's like the middle potential he used or the endpoints, but the point is you could just say like, okay, you can read up here, see where my mouse is. You can see the Y value. So in this case, the lowest potential is like minus 0.201 and the highest one is minus 0.1680 or whatever. Okay. So I might say, for instance, that one of the answers for like where should my data is that I've bless you, used my Tafel slope that I know I want of 120, 118, or whatever to inform where my potential, where should I take my Tafel slope. So that's one way to kind of do that, right? I could also like, move this around and say like, oh, well, that's 90. So maybe that's too low. Or if 90 was my answer for whatever reason, or 60 was my answer, this kind of tends, and don't worry about this data. This is from whatever I did. It doesn't matter. But if it was 60, I might be able to say like, well, it's 60 here. It's 60 here. If that's a 2 electron process, it's 60 here. So I might be able to say like, okay, well, if I go anywhere beyond here, so like this right here is minus 0.13 or 0.13, and up here it's 0.9. So that would be where my potential range is, and I'm using, changing my slope actively to see based on my potential limits, how do I get a Tafel slope of interest that I know I want, right? So that's a way to kind of do it. And actually that's, again, always strongly point out that Tafel data is not just current and potential. It's kinetic current and potential. So to a very, to a lot of researchers, folks do this all the time. They take an LSV or a CSV and they just scan. They do HER, they scan negatively. They do OER, they scan up, and they get a current, and they just like, I'm going to make a Tafel plot. And it's like, that's not a Tafel plot. It's just not. Your current is not kinetic current. It's, who knows? It's a lot of stuff, right? There's a lot of stuff involved, but it's not all kinetic current. And if it isn't all kinetic current, the Tafel plot doesn't mean anything. You might even coincidentally get a Tafel slope over some range. So you just have to be really careful about this. I say this all the time, partly because it's like, well, it's funny, but also it's true, right? I mean, you don't want to get data, even if one of two things will happen, and neither is good. You take data that shouldn't be made into a Tafel plot because it isn't pure kinetics. And you're going to get bad results that make you wonder why your Tafel slope is bad. Or you're going to get coincidentally good results that lead you down the wrong path of thinking you have a Tafel slope of something. Both of those are incorrect because you shouldn't have made the Tafel plot in the first place. So there's ways of getting around this. People do rotating electrodes, rotating disc electrode, RDE and RRDE experiments are a way to deconvolute mass transport from kinetic current. Levitch and Katecki-Levitch analysis allows you to do that. That's one way. Beyond that, it's like very, very painfully slow scan rates. That does theoretically allow you to minimize capacitive effects. It doesn't necessarily allow you to eliminate mass transport effects, but at least the capacitance will be relatively minimized. So some of this non-Faradaic kind of, surface charging can be minimized to allow you to assume in some cases that it's mostly kinetic current. So, the farther you deviate from the, on the potential axis, the more likely you are to have convoluting effects. So there's a lot there, but the point is some of those are strategies where you can try to assume that it's mostly kinetic current. And then maybe best case scenario, I would say, is that, you can make a Tafel plot, and even if there's some error, it's minimized as much as possible. But I see a lot of people that take 50 millivolt per second CV, and they just make a Tafel plot, and it's like there's no meaning to whatsoever. Done. There's no meaning whatsoever. You might as well just change the units to something for no reason. There's no meaning. You know what I mean? This is not a real analysis. So just try to understand a little bit of the theory. But once you have done that, again, I like this approach, even if it's almost like backing out your answer. I like it because it's it allows you to look at your data critically, knowing what a Tafel slope should be, and then find your voltage limits, that way. And hopefully, what it means is that the voltage limits you discover correspond with an overpotential for the OER. So the OER happens at 1.23 volts versus HE. So I think in that case that might have been that because it was 1.4 or whatever. If you do this and you're finding your Tafel slope at 0.9, something alarm bells should be going off in your head. It's well, I can't do OER at 0.9 versus NHE, right? It's I'm not a high enough potential, so that if I do this and I get a Tafel slope of what I expect it to be at 1.4 volts or something, it's well, that makes sense. I have an overpotential for OER. I should be doing OER. This kind of works. This kind of makes sense. So you can kind of use some of a mixture of empirical, working this out, and theory and knowledge of electrochemistry. So there you go.
Well, Alex does have just a quick follow-up. So while we have Alex's attention, Alex just says, thanks. Could you also please explain how to get exact onset potential for OER and HER? It's kind of
it's subjective.
It is a little bit subjective because you're looking at a sloping line go up, and it doesn't just it's not just like a complete vertical step, and you have a very precise potential. You do have to take some liberties with it, but it should only be really a few millivolts at best, where the onset potential really starts to come. A lot of people, what some people typically do to kind of overcome, reporting the onset potential, is they just describe what is the potential at like 10 milliamps,
Yeah.
or something like that.
Having a real metric can help.
Yeah, and that's just a lot easier because there's only one voltage at a particular current, and this and yes, maybe you can't get to 10 milliamps, but maybe you could get to 1 milliamp or something like that. It at least creates a better benchmark than like guessing where the onset potential is. So I would do something like that. I would just report what your voltage is at 10 milliamps per square centimeter or something like that.
Yeah. Having a metric for it, like you said, it's you're going to have to do it that way, because otherwise you have this subjective nightmare. Because it can look something like this. Like here, this is like RRDE data, but it's like, okay, where's my onset potential for the bottom curves? Forget about the top ones, right? Let's do this. What am I trying to do?
Right click hide.
Yeah, the hides. Yeah. Here. Hide titrate. I want them to go away, because I don't even want you to look at them. They're not here. I just decided last minute I don't want you to look at them. Okay. So just consider the bottom traces. Where's the onset potential, right? Is it here, here, here? And guess what? That's going to depend on how zoomed my axis is. So if I zoom my axis, it's like maybe I'll say it's here, or it's here, or it's here. But if I zoom way out, it's another point. That's the only other point I want to make. Is like, even how visual your like zoomed your axes are will impact your ability to feel like, oh, this started curling down, way back here, actually. But when I'm zoomed way out, it's like it doesn't look like it's curling down until like here. You'll have like 50 millivolt difference just depending on the scale of your darn y-axis. Like it's an annoying. So to Alex's point, you want to do one of two. You need to have like a metric. Like, okay, well, what my metric is when the current hits whatever, compared to the baseline. That's when the onset is. Or you do a derivative thing, which is, derivative measures the slope, right? So you could say something like I don't know if this is going to be a good idea, but
we're using our math transforms.
Yeah, I could do like a differentiation thing. I don't know if this is going to make any sense, but this is one way you could do it. For instance, this is like the peak like derivative. Forget about the unit is, it's silly. It doesn't make any difference. The point is, this is the derivative of the curve. So this is how the slope is changing. Now this might correspond with the middle of it or whatever, so that's probably not accurate, but you could say like where the derivative actually, hits some value. I don't know, maybe this is the value, like where the change in the slope reaches some point could be your metric. So, and you could just, it doesn't almost matter what it is. You just make sure you apply the same metric across the board. So it's like whatever the derivative, again, this is arbitrary, hits some value, just like, 10 milliamps per centimeter, it's arbitrary. Then that's where, you could just, for example, say, that's where I'm going to say my onset potential is. But the key is just applying some metric consistently across the board so that you're comparing the same things. That's kind of how I would, I don't know.
Yeah.
Suggest you do that, but it's tough. So. It is a tough thing. I will acknowledge. So
yeah. All right. Seth asks a question. How do I use CV to know deposition potential to co-deposit two metals? So typically, see, maybe I know this. So if you have a solution, or if you're doing CV, so typically, let's see. So when you're doing a CV, you might typically be doing some kind of reduction. So I'm going to put this in like a negative voltage range. So what you might have is as you're sweeping the potential, you have like, near zero current, you then all of a sudden get this like reduction current, and maybe it flattens out. Maybe it doesn't look very perfect because it's a deposition. But you will start to see, a peak, something maybe like this or something like that. And then this corresponds to one metal deposition. And then, you know, similarly, you do a peak and then it's like, oh, it's over here. So here you now have like the potential for, you know, reduction. You would, of course, if you do get a CV, you would want to use kind of like the E1 half between the two peaks, um, the cathodic reduction and the anodic. You might pick the halfway point if you are able to get like a stripping as well. I know that when you deposit metals, you end up getting the voltammograms look a little bit weird. It won't necessarily be a nice peak or something like that. But you can say you can also just report peak potentials. Those are usually perfectly good. We just talked about onset potentials. You can report an onset potential by guessing approximately, oh, it's around here. That's where you start to, this is where you start to get the metal deposition. Now, when it comes to co-deposition of two metals, it does get tricky if you do put two metals down and then you're trying to figure out, well, which one is which. Because what you may observe, and I'm going to just kind of draw this, I'm going to redraw this, is you'll probably observe something that might look like this, where it goes down and then it kind of goes down again. So this is a CV that has like, you know, maybe you'd say like it has two steps, and the current never kind of returns fully. You have a background current associated with the deposition on top of from one on top of another. And typically what because here's the thing that I think tends to be a little bit tricky as you're doing science on this subject, is you're gonna have metal A and you're gonna have metal B, and you're gonna have substrate C, right? So maybe C is carbon or something. Well, you can have a variety of different, you know, situations. You could have you can have A, you can have a layer of A on the surface, and then you can have B on top of it. That can happen. You can also have a situation, actually, well, maybe. Again, you have this, and then you have B, and then maybe you have A on top, or A on top. And the potentials of like A bonding to C, and the potential of B bonding to A that's also bonded to C, and the potential of B bonding to C, and the potential of A bonding to B bonding to C, like these are all different, right? So this is where you get like under potential deposition or over potential deposition. It all has to do with these kind of interesting situations where you're depositing a metal on something with different electronic affinities, so that, you know, because if you were to plate, say, A on top of A, there's a potential associated with that. But maybe you have an under potential deposition if A has an affinity for C and you're actually depositing A on C at a lower potential. So this is when you have metal deposition, you may have to run into situations like this. Now, sometimes your system is like very reproducible. When you have a soup of A and B, it always forms A and then B. That this is like not thermodynamically favorable, or it's a very unlikely configuration, or you don't get like an alloy or something like that. And the waveform of the potential that you apply for the deposition will affect how it actually forms. But generally, what I mentioned, so I just mentioned those things because the potentials that you observe for these points are going to depend on this configuration, because you can look in the literature to kind of get an idea about, you know, bonding strength and say, oh, oh man, one of these is going to be bigger or smaller than the other. So I would expect the thing that's easy to bond to happen at a lower voltage, and the thing that's harder to form a bond to say happen at a more negative potential for the reduction. So those, I only mention those as things to think about and consider when doing a co-deposition, and of course doing experiments where you're testing these. Like, you just deposit one, you just deposit the other, and then you add the other one, and vice versa. You don't have to just make it a soup initially and then just apply a potential, because then you have no information. So there may be a series of experiments that you need to do to get a better idea about what's actually happening when you and get useful information from the CV about the potentials for deposition. I will also mention one last thing, which is that you may decide to do something like a galvanostatic experiment, where you set the current and then you observe what the potential is for the deposition. That's actually because that allows you to get a reproducibility in terms of the only plating just one thing. Because when you're sweeping the potential, a bunch of stuff can happen. You will be co-plating both of these things in different orders. But if you say, oh, I only want a very low current, just give me the voltage required to only get a constant current, and the potentiostat will adjust it. So you have some options. It's not just CV when looking at depositions. So Seth, hopefully that's helpful. Let us know if you have any further questions about that.
Very good. I was just trying to go through some of these numbers Yogesh is mentioning.
Yeah.
I was just preempting some of you. So
yes,
Yogesh's question here. Next question is: my working electrode is nickel oxide decorated laser induced graphene. Also, side note, my favorite Halloween decoration: nickel oxide.
Decoration.
It's a decoration. While doing CV, it appears additional peak of nickel oxide in additional to the ferro probe. But the additional nickel oxide peaks in the CV appear only at a higher drop casting concentration. So you're saying 50 microliters of 10 milligram per milliliter. However, the additional peak of nickel oxide does not appear in lower drop casting concentration. So you're saying 50 microliters of 1 milligram per milliliter. Could you explain why this happens? Okay, well, first of all, I mean, it just a simple math. I mean, it's actually pretty simple. 10 milligram per milliliter is 10 grams per liter times 50 microliters gives you 50 micrograms times 10, which is 500 micrograms. So half a milligram of nickel oxide compared to 0.05 micrograms, your 10x difference, right? It seems to me like the most obvious answer is you've hit a detection limit. Like when you have 500 micrograms of nickel oxide, it is apparently enough nickel oxide to observe a CV wave, right? You've deposited enough nickel oxide such that when you scan, presumably positively, that's where nickel oxide has an oxidation peak, you'll observe the redox behavior. But when you decrease the amount of nickel oxide that you're adding by a factor of 10, you simply don't. That likely, just to me, means that you've hit a detection limit, probably for your instrument. I suppose it's possible if you had a potentiostat with more low current resolution or something, or lower current range, or it's in comparison, let's just say, with the ferro. So if you have like 0.1 molar or 0.05 molar, ferrocyanide or something like that, this is pretty typical in solution. The current you get for your ferrocyanide redox, you might actually have a peak for nickel oxide. It's just so small compared to the peak of your ferrocyanide. And if the current, the amount of material you have will be in proportion to the amount of current you get from it, right? So it's like if you if the ratio of the current, which would be seen in the peak height, to make it simple here, if the peak height or the amount of current you get for the ferrocyanide redox is like, I don't know, 10,000 times the amount of current that your nickel oxide will generate because of how little micrograms you have there, well, you're just not going to see that peak. Like it's, you might be actually doing your CV and your software shows you a big peak for ferri, and it's like when you hit where the nickel oxide happens, it actually did oxidize, but it's like one DAT count blip, and the current range you're on in your potentiostat is just not going to measure that, right? Like if it's, I'm just make up numbers here out of nowhere. Like if it's like 500 microamps is the peak height, right? Let me share a thing rather than air draw now. If I'm talking about numbers here, right? Let's say you're doing your ferro. Where's it happen? Like 0.10, something like that. I forget.
We in an aqueous buffer that he has.
I guess. Yeah. I forget what that happens. Maybe it doesn't matter.
Oh, so ferrocyanide.
It's like slightly above 0.
Well, okay.
Maybe it doesn't matter. Maybe I'll just pick it up.
It's oxidation, and you can just like
all right.
positive point.
So like if this is your ferro, peaks, I'll just ignore where this ends for a second, right? This is your ferro redox peaks, and this value is like, let's just say 500 microamps, like I was saying. Okay, whatever. That's just the number, right? Well, your potentiostat, let's say to measure 500 microamps, might be on a plus or minus.
No,
I got it.
Oh, you got the fruit fly.
I got the fly. It's been here for like 3 months. I swear.
Yes.
I finally got it. Okay. Your potentiostat might have a 1 milliamp range. Okay. Let's say it's on the 1 milliamp range, right? Well, as a company that makes potentiostats, I can tell you, when you're on a range of plus or minus 1 milliamp, your potentiostat can measure 500 microamps. It could probably measure 1 microamp. It could probably even measure like, let's just say 100 nanoamps. Like, okay, like you start pushing the limits, right? But as soon as you start going down in current, we have a frowny face. You're just not going to be able to measure, because the reality is that it's actually just simple mathematics. I can do it really quickly, but it's like, what is it? 65,000? Is that?
Yeah, about 65,000.
Yeah.
If you have a 16-bit DAC.
Exactly right.
Yeah.
So 2 milliamps divided by 65,000, whatever. So it's 3 times 10 to the minus 5. So it's 10 to the minus 8. It's like 30 nanoamps. So in other words, the minimum step size is around, let's just say 30 nanoamps. That's an N, right? So even 100 nanoamps is probably not going to be all that great. So if I'm on the 1 milliamp range, if I have like digitized signal and I'm measuring my current over time, whatever it is, the best I can measure is like 30 nanoamp steps, right? So if my nickel oxide concentration is so small that I'd have to like that's what it would be. And I like zoom into this, right? And I would just have an inset, right? And I would zoom in and I'd be like, well, actually this is my signal. It's like, it's actually a peak. Like, why aren't I seeing it? And it's because this, difference is like 1 nanoamp, because I only have a 0.05 milligrams of solution. It's like, I'm not going to be able to measure this because of the current range I'm on, because the resolution, I just can't measure it. It doesn't mean it's not happening, but I would need to go to a much lower current range, like a plus or minus 100 nanoamp range or something like that, like down in current. Now that would mean that I can't measure 500 microamps. You see, I can't measure both of these things at the same time. Now, if I don't have my ferrocyanide, maybe I can measure this. Or if I just want to ignore my ferrocyanide, what I'm going to do is I'm going to get like I'm going to give this peak a haircut. right? And then when I get to my nickel oxide, well, I'll have nice resolution on this small peak because I'm on a low current range, but I'm probably just drowning out the signal. It's just a resolution problem. Or it's a actual physical problem that that little nickel oxide, somehow like the microstructure of my catalyst. Let's say I have, you say, is it a carbon thing? Or it's graphene. Okay, so you have a carbon layer, and you're sort of depositing, nickel oxide. And it's like if you have so little bits of it that like the nickel oxide is just like somewhere in like there's like 5 nanoparticles embedded within your, graphene here, right? This is your graphene. It's like it's not even accessible from the electrolyte. Like I can't even get to it. Well, then I'm not going to have any electrochemistry associated with it at all. Like until I have enough nickel oxide deposited that I actually get some at the surface, like nickel oxide, at the surface, then I will start seeing some electrochemistry signals from it. But if I don't have enough at the surface, it's either that my potentiostat can't measure it for the reason that I described, or I just don't even have enough for any electrochemistry to even happen in the first place. But either way, this just sounds like a limit of detection thing. Like, at some point you're going to have so little material there that either it's not reacting much at all, or you just can't measure it.
Yeah. Also, CV is one of the few analytical techniques where like background current can become
that's a good point.
is actually like big. I have two suggestions. I think Neil makes a great point with limits of detection. Literally setting the current range for some of these experiments may be able to give you nickel oxide detection. Two suggestions. One, try a technique like differential pulse voltammetry. Or square wave voltammetry, because those techniques by design remove non-Faradaic as well as even Faradaic background current. So you'll be able to see, so hopefully the nickel oxide peak can be observed. The other thing to do is, if you're really worried about it, do a titration. So simply continue to add 50 milliliters of the 1 milligram per milliliter. And then you'll find like, oh, after I add 3 of them or something, I'm able to, now I see the signal, because you've gone down by an order of magnitude, 10x. And it's like, oh, once you add a little bit more of it or enough of it, then it is a limit of detection, and you start to see the peak. It starts to come back again. Of course, keep in mind, you keep changing the volume of the solution when you keep adding this. So just keep that in mind as you're doing the experiment. But yeah, that's my other just 2 cents.
Yeah, that's a good point. Yeah, DPV or square wave, but DPV is a good one.
Yeah.
Pulse will definitely help you clarify some of that, whether you have it.
Yeah.
You do CV, you won't see any peak, or it's hard to clarify. Then you do DPV and you get like a nice looking peak, and it's like, oh, yeah. That's a good way to take the background out.
Yeah, or just the scan rate.
Yeah, that's
CV.
too.
That's another thing you can do.
Yeah, slow down your scan rate. Yeah. Decrease the background.
Mm-hmm.
Yogesh has another question about his nickel oxide decorations. And I too enjoyed nickel oxide decorations. That joke is going to continue. During EIS measurements for my nickel oxide laser induced graphene working electrode, I think my problem is I don't know. I don't know what you mean here. My visualization is I can't figure this out. So he says the impedance value decreases abruptly at lower frequency region and then increases linearly on going towards higher frequency region above 45 degrees.
Yeah,
could you explain why?
There's got to be a.
I'm trying to picture. Well, you're talking about. It's almost like I'm just confused because you're talking about. Okay, it sounds like you're talking about an impedance magnitude. I'm going to try to draw this from what I'm reading, and Yogesh, you can maybe comment if what I'm drawing is correct or not correct. And if it's not correct, the answer unfortunately might just be, I would need to see your data, and I can't easily. I know, and my apologies, because you are certainly doing your best to explain in words a graphical, anomaly, and this is not easy. So I sympathize with you. But I'm just going to try to think this through as I read. So the impedance value decreases at low frequency
abruptly,
and then it increases linearly towards higher frequency. So impedance decreases at low frequency. So it's like if I have some
So we're looking
impedance
at a Bode
magnitude,
plot
yeah,
for this.
yeah. So this is impedance magnitude. Now, usually the impedance does go down as the frequency goes up. So again, I'm heading back and reading it. So the impedance decreases abruptly at low frequency, increases linearly going towards high frequency. But see, again, above 45 degrees, but that's a phase angle. So I'm a little confused because you're mixing units here. You're talking about the impedance and then you're talking about a phase angle. So I'm not sure I understand. But basically, if you have something where it's like the impedance is decreasing, over this range, right? The impedance is going down, and then the impedance goes up at a high frequency. The only reason impedance can go up, it's your favorite, Alex. It's an inductor. It's just mathematically. If I just look at the mathematics of a capacitor and an inductor, Z is equal to 1 over J omega C for a capacitor, right? And so what this means is that for
he's all right. So he's clarifying a little
Okay,
bit.
yeah, please.
He says, "I meant for Nyquist plot for EIS." And
Okay,
if I had to guess,
okay,
this
so
is
let
this is
me
what I
abandon
think.
this drawing then, because you're talking about negatives. Yeah, tell me what you think.
So I think think of it as like a regular semicircle in
Yeah.
the beginning, high frequency.
Mhm.
But then instead of it going down normally, it like sharply, it's like a data point was missing.
Like something like this almost.
Yeah, something like that.
So it drops, and then what's the 45-degree part? Because the other part, I think you're mixing which is high and which is low frequency, because you're saying going towards higher frequency. I think you mean lower frequency.
Continuing lower frequency.
Because as you go this direction in the Nyquist plot, as you go to the right, it's lower frequency.
Yeah. And then I think what's happening is you can draw the 40, you can draw the 45-degree line, but you could draw at a higher angle, so it's more capacitance.
Something like that. Yeah.
Something like that.
So, yeah, this might not be exactly what you're
Yeah.
seeing. You can comment if I'm even in the ballpark, if I'm even close. So first of all, if you have something like this, yeah, that's like an anomaly. That's not a real impedance. Like if you have any sort of discontinuity, where it jumps like this, maybe you just have a point here and then you have a point here. Something is funky going on, but almost for sure, an abrupt move of data point like this is not science related. It's not a phenomenon of your electrode. It's not a phenomenon from the electrolyte, anything. It is one of a few things. It's the potentiostat doing something bizarre, like it changed a current range on you or it changed a gain setting automatically. And sometimes you have a weird discontinuity. That can happen sometimes. Sometimes it happens at high frequency. You'll have like a high frequency data where you get like this weird artifact happen. And then it's like your data will start like here. And then it's like your data is normal. It's like, what is this? It's like a jump from here to here, like that kind of happens sometimes. And it's like, the answer is ignore this garbage. It's artifact. We call it artifact because it's a response from a number of possible things, but none of them are science and we just don't care. So this probably isn't exactly what you mean. But anyway, the point is if you see something like that, an abrupt move or whatever, you might have to take your data again. You could, exclude this single data point if it's just one data point and it pops back up. Like, it's not a feature you want to analyze is kind of the main point that I want to make. On the other hand, the last part of your point, again, if I'm understanding it properly, is that you can have, for instance, features on the end.
He has another thing. Let's see. He says it's coming a kind of inverted circle and then increased linearly. I don't know.
It's like that. Is it a loop?
Yeah, is it a loop?
Is it an inductive loop? Alex is going to quit on me.
It's like, I thought I had. Nope, I don't know. Well,
inductive loops are a thing.
Inductive loops are a thing.
It happens.
Yeah, does it curl?
Yeah, does it curl?
I mean, that may be what it is.
There's an answer for that, and it's not a good answer, but there's an answer. And then if you're wondering why is it, 45 degrees here, right? That's infinite plane Warburg diffusion. If it's a higher angle, the best way I try to describe this is it's like 90 degrees like this, that's capacitance. That's a perfect capacitor, right? 45 degrees is like infinite plane diffusion. So 75 degrees, 80 degrees, 90 degrees, whatever, not 90, 85 degrees, whatever, anything between 45 and 90 degrees is something between diffusion and capacitance. There's two ways that I think about that. One is that a capacitor is two perfectly parallel plates. But what if my electrode surface is actually some heterogeneous surface, which it of course is technically if you zoom in far enough, right? This is my electrode surface, but it's not a perfect plate. Well, sometimes people have used this as a way to explain the non-ideality of the capacitance. It's not exactly 90 degrees because it's like it's capacitance, but it's like at a rough surface. So the degree to which the angle is less than 90 degrees is the degree of like heterogeneity. The other possibility I like to point out as one is that you can imagine if I have my electrode surface and I have, my ions, they're actually quite close. This is the inner Helmholtz plane. Let's just say this is my capacitance, right? This is like plates, two parallel plates. But let's say this side of the plate is diffusing slowly. It's moving. Well, is it capacitance or diffusion? Well, it's kind of both. It's like a capacitor where the distance in between the two plates, right? D is going up over time. You could imagine, right? That the ions are diffusing away or something like that. Like that's a possibility. So it's like a capacitor that's changing. So that's one possible explanation I give where it's like, oh, well, it's like, maybe it's like 55 degrees, right? It's like, it's a little bit higher. It's like diffusion, but there's a time element to it. Alex talked about this. It's like 45 degrees is like a perfect plane moving in space and time. And like, if it's a higher degree, it's like it's taking longer for that plane to move the same distance, right? Because that's the y-axis is the time component. So those are just
that's a way of thinking about it.
I love that explanation, by the way.
It's like it's like there are many systems that have this kind of feature, but it's like the frequency with which those things are taken. It's like, well, how long does it take for the charge to get there? And it's a function of like the distance. But yeah, it's like you have a boundary. It's like it's always defined by like a set non-absorbing bound. I never get those.
Yeah,
never get this right.
Because I come from an engineering background, we call they have like names. There's like Dirichlet boundary and Neumann boundary. These are whether it's like it's like first, second, or it's zero, first or second order derivative. Is what it actually is mathematically at the boundary, and it's whether it is absorbing, like reflecting, or non, or there's nothing there, like like it's zero, like the concentration zero at the boundary, something like that. So there's I did all of that in as an undergrad. I actually love it. This is one thing where I do remember to some extent, although specifically I'd have to look it up. I like math. I like math. Like there's an elegance to math that I enjoy, and that's actually what leads directly into the derivation of the Warburg short and the Warburg open that I never actually talk about because it's boring mathematics and we pretend that doesn't exist because we're chemists. But the reality is the difference between the open and the absorbing and the Warburg short, Warburg open. It's just a boundary condition. It's like a first order derivative versus a second order derivative, something like that. I digress a little, but
so I think so now that I've thought a little bit about this. So now this makes a little bit more sense. I think he's got a little bit more of a 45 degree angle, and it's pure Warburg, because when he describes his system, it's graphene with nickel oxide on it. Right. And so if it's like, all right, and if he's looking at paraquat or anodic stripping voltammetry or something like that, it's in solution. It's just in a freely so he doesn't have any boundary conditions, most likely 45 degrees, but he's seen an inductive loop because because probably the amount of nickel oxide he has is a very thin film, and you can get these inductive loops associated with like the kinetics of electron transfer changing because he's looking at the charge transfer between like the graphene and the nickel oxide, because it's not like there's charge. It's not like it's charge separation like a capacitor. You're actually able to get electron transfer and change in oxidation states. It's in Mark Orsum's book. I gotta learn a little bit more about it.
I just think it's amazing that you openly advocated for the existence of an inductive loop.
Well, yeah, because
is like growth. It's like personal growth.
He ends up finding. So Mark Orsum says that the value of the inductor, when you invert it, it's equal to some blah 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 bunch of stuff. But then there's a kinetics element only with these thin films on.
It's
on
a blah blah blah. Who cares?
It's a blah
inductive loop.
It's a blah blah blah. Who cares?
It's
inductive
often
loop,
meaningless,
but it gives you a value.
The value is often meaningless.
Well, Yogesh, you're welcome. Hopefully it's helpful. We're trying to,
and ultimately, at some point, if you're still struggling, reach out.
Yeah.
Through email or something like that, you could send an image of your Nyquist plot. It might be, if what we drew is close or if it's like nowhere near it. Yeah. Seeing is believing, right?
Seeing is believing.
To see your data, I would have a little bit of a better probably grasp of what you're actually seeing, and maybe have some more comments after then.
Yeah, it's difficult to describe a Nyquist plot with words.
I know. So I sympathize with your plight of trying to get advice while trying to describe a Nyquist plot. Not the easiest thing. So okay. Ditto says, I want to use ITO plates in place of glassy carbon electrode. Would it be a good choice? Maybe. I mean, it depends on your application, right? ITO is used a lot of times for like photo
electrochemistry.
Because
conductive glass almost.
Exactly. And glass, it can be optically transparent. As a general, answer, you can't really give one. It's not like, would it be good to use ITO instead of glassy carbon? It depends on the application.
Yeah.
Right. As much of a general answer I can give would be this. ITO will be harder to use than glassy carbon, almost for sure.
Yeah.
And the reason is that glassy carbon, while not technically a metal, acts like a metal. Okay, which means that glassy carbon as a disc, as a sheet, as a rod, a plate, is a solid material that looks and acts like a metal, that you can clip to, use in a disc electrode, rotating disc electrode. You can use with an electrode holder. You have options or whatever. But just like a piece of platinum or a piece of palladium, whatever, you can use glassy carbon in pretty easy, to manipulate and connect to ways. ITO does not usually qualify under any of that description. ITO is usually a film that's deposited onto a piece of glass or quartz. Okay, so what that means a couple of things, right? ITO, indium tin oxide, is electrically conductive. I think it's a semiconductor technically, but it's electrically conducting, right? And it's also a film. It's not a standalone material. It's not a metal. It's not something that you can get like a rod of ITO. It's like that would be a rod of glass with ITO, deposited onto it, like vapor deposited or something of that nature, right? It's not a solid material. Glass and quartz is an insulator. It is not electrically conducting. So fundamentally, ITO can be tricky to work with because you're making electric with it is not always easy. You have to use some sort of conductive tape or glue or something onto the glass where the ITO is. That can sometimes make the setup and connections a little tricky and difficult, right? In a vacuum, I would say, when you're comparing it with glassy carbon. Now, of course, systems that use ITO regularly, they've found a way to do this and it's fine. But if you're saying like, well, I'm using glassy carbon for this reaction and it has this morphology, this size electrode, and I'd rather use ITO, it's like, okay, you're going to probably struggle a little more to make electrical contact. If it's a piece of glass, it has like sharp edges, right? With glassy carbon, it might also have sharp edges, but you can make contact to like the back side of the glassy carbon while the top side is in contact with your solution, or the other way around. You can make contact with the top and the bottom is the electrode part. Well, if you have a piece of glass with ITO, even all around it, you have to hope that the ITO is continuous along that sharp glass, edge, because the glass itself is not conductive. Like electrons aren't going to move through the glass. They can't. It's an insulator. It has too wide of a band gap. So the ITO or the FTO has to be like going around a sharp edge, or you have to snake a piece of conductive tape all around. Like, just, I guess that maybe I can stop here. It's just, the point is that the contact is trickier. It can be harder. You have to make sure you have electrical contact everywhere you want it on your ITO. So as a general rule of electrochemistry and electrodes and connecting and the whole experimental setup, ITO can be trickier to work with. So I hope that's kind of clear. And again, it would depend on the specific application you're studying and the specifics of your experimental setup, like the geometry, literally, like how big is the thing you're doing? How big is your cell? How much volume is it? What's the working electrode dimensions and everything, whether it would even be possible. So those are sort of, I don't know, overview, I guess I'd say, of ITO and that as a working electrode there. So
yeah,
you can follow up if you have any further questions about the use of those.
You can also
electrodes.
answer her
yes
next question, which is, can I use CV for drug degradation?
If it's less,
oh, sorry.
Yeah. I mean, if the drug is electroactive and has
Yep.
a redox reaction that it corresponds with degradation, then yeah,
like oxidation or something like that. Yeah,
for sure.
Yeah, it definitely can. I think there's, there's a whole electrochemistry community I know of, like a neuroelectrochemistry, where they're looking at, like dopamine, which isn't a drug, but it's just to say that there are organic compounds, which could be drugs, that can oxidize on an electrode surface, and you can detect those using cyclic voltammetry.
Yeah.
So yeah, absolutely.
Yeah, and I guess the other part of this is like use CV for drug degradation to like if it's electroactive, you can use CV to determine or detect, the potential, let's just say, at which that happens or something like that. But it depends on what you're after, right? If you're after degradation, there's a lot that you can say about like how this sort of subset of electrochemistry, like degradation, sometimes is done by applying a potential or a current or something over a long period of time and seeing how it changes or degrades. Or you're doing a lot of CVs in a row and seeing how the peak changes. That's a way to see how something degrades. So can I use it for, like, yes, but it depends on really what you're looking for. Sometimes the CV is just for detection of a peak or the presence of any kind of reaction at all. But the degradation, you might use a different technique. Like, to look at the degradation and study it, you might use a slightly different electroanalytical technique in addition to CV. CV is just a good, like, I don't know what you say, like exploratory kind of a technique to see if there's something going on, right? It's very easy, relatively speaking, to set up a system, a cell, and just kind of sweep the potential around and just see what you see.
Yeah.
Yeah. It's
Absolutely.
like, can they help me find the potential window?
Yeah, absolutely. Yeah. Oh, no, we're not gonna, well,
I'm like,
potential window.
We haven't had a question about that today.
Yes.
It's amazing.
Yes.
We haven't had a question about where impedance should be done.
Yeah. So we're doing good.
Doing pretty good.
We did get some inductive loops,
and we did get Tafel.
We get some Tafel. So
there's really never a clean day for you and me's mental health.
Yeah. It's like people need to ask questions like, can you explain IR compensation?
And you're like, oh, can I?
Oh, can I?
I
can do that.
So.
That's
and someone could be like, could you tell me about batteries and C rate? And I'll be like, I sure can.
Yeah, sure.
That's like our happy place. We just talk about that for 2 hours. I'm very happy.
Yeah.
You don't get to pick the questions. You just get to answer them. That's our job.
Yeah.
We don't get to. We're happy to take all of your questions, even if inside we're dying a little bit.
which is okay.
It's
I mean,
fine.
it's important. Hey, the more of these we get, it's fine. It does challenge
us. Is it
us.
important though to like die on the inside during our workday? Is it important?
But it is, it's a thing.
Builds character.
It builds character, but I think it informs us that like, oh man, we really need to make it easy in our software and explaining things. That like, hey, people want to be able to do Tafel slopes, and we need to add a software component where it just says no.
That's I was just gonna say that. I'm glad you went there. That's right. People want to make Tafel plots, and we need to make it harder, so they don't make it because it's meaningless.
Yes,
and that would be just the best way to go about it.
Yes,
that's a way to sell equipment, is to deny what people want to do. Right? Just don't let them do it. That's reverse psychology. Like, we did have
an engineer at one point who, as a placeholder, when you clicked an experiment, the angry like frumpy cat would come up and just say no.
Say no. Yeah, it's like, can you perform my cycle of temperature? Just go no. And it's like, but I wanna. Speaking of wanting to do electrochemistry, Quasi Benazir says, "What's the whole topic and contents within electrochemistry?" So let's just do all of it right now.
Oh yeah, I think we could list a ton of stuff.
All of it. Let's do all electrochemistry.
So, well, okay, I'll say this. There is the topic of quote physical electroanalytical chemistry. That's like 90. I just listed 90% of Barton Faulkner right there.
That's correct.
I just said that. Like most of the book is done.
That's right. All of Barton Faulkner.
That's almost all of Barton Faulkner is physical electroanalytical chemistry.
That's true.
And then the other two things he's got in there is like chemiluminescence and then electrochemical scanning, microscopy. And then there's the whole other side of electrochemistry. There's the impedance, there's corrosion, batteries. You know what? No, here we go. Energy storage devices. There. I just covered batteries and fuel cells, supercapacitors, pseudocapacitors. All right, that's all done.
We did. We're getting there.
We're getting there.
We're covering all of our entire discipline.
There is corrosion.
Incredible.
There's electro winning, which is something that I learned about. That's about electrochemically getting.
I still don't know.
Oh yes, you can. It's about removing minerals from ore electrochemically.
Oh, that's right.
Which
every time I see that term, I'm just like the word winning.
Yeah,
it throws me off because I'm just like, am I an electro loser because I don't understand how this works? I'm an electro loser because I don't know what electro winning is. I guess I'm electro losing. I mean, the jokes write themselves, but in addition to that, I don't. Yeah, I don't know.
And then conversely, there is electroplating. So it's like you can strip stuff out, metals off of a material, then you can put them back onto a material. And then a lot of electrochemistry is actually just synthesis of new materials, like new electrolytes, new electrodes, stuff like that for different applications. So I would say that's mostly. Let's see, there are electroless depositions and stuff, purely solution phase stuff. Oh, catalysis, electrocatalysis. Boom, that's it. And then I think that's everything. I think that's every topic in electrochemistry.
We have covered the entire thing. Let's just shut it all down. We're done. We covered everything.
Molten salts. So that means high temperature echem, low temperature echem. Okay. High pressure echem, low pressure echem. Echem in space, echem on planet Earth, echem in the core of the Earth. So echem in all locations.
I love echem in space.
I think
we should make a movie called Echem in Space. That would be amazing. What is the whole topic and contents? This is I feel like we spent a lot of time on this question, and I'm not sure it was even meant seriously. Maybe it was. But I guess the real answer, honestly, is that electrochemistry is something that people spend many years studying, and it's really hard to just give a perfect answer. But hopefully, Alex just laid out a lot of the subtopics, maybe that are part of it. So there's that. I guess that makes sense.
I think that's the most stuff.
Just every single topic.
Every single topic.
Well, anyway, we've now that we've taken a stroll through all of electrochemistry, I can get to Tamogna's question, which is, "Hi guys, recently I was asked why does current Why does current increase with scan rate in CV? Okay, I can explain that mathematically bit. What is the physical significance? Also, why is it proportional to the square root of the scan rate? So I thought what I would do is just show you this one slide that I have that I made sometime last year for a seminar that I have struggled with this actually, because I also, like you, Tamogna, I really desire an explanation that is not just because math says so. And I'll be honest, most of the answer is because math says so. I hate it. I wish there was an easier way to like intellectually answer this question. There probably is a good answer, and I have never seen it. And I can try to explain why I think maybe I can answer in some ways. So this is just one slide where I talk about scan rate influence on current, right? This is your whole question. And so basically the peak height and the background current, but current in general increases with scan rate. So the first sort of answer I have here is right here, which is that the scan rate, this should be dV/dt. This shouldn't be dq. That's wrong.
Nice.
Yeah, so there you go. I'm glad I presented the wrong thing. Now that I'm looking at this in retrospect, that was silly. No, wait. dV/dt is the scan rate.
And dq/dt is the current.
Yeah. Maybe I did mean dq/dt. I'm trying to think what I meant here. I just took this one slide out of context, and I'm trying to remember what I was meaning.
Yeah.
dq/dt is current. Yeah, I'm trying to think what I mean. Yeah. No, I did mean dq/dt. Okay, so I was correct. dV/dt is a scan rate, but what I here's the thought. Okay, so see, this is why it's hard. I've had a hard time explaining this, admittedly. When my scan rate is large, right? And I'm just sort of reading my words here, but the point is, I'm changing the voltage over a shorter period of time. Like I'm going from 0 millivolts to 50 millivolts over a shorter period of time. I'm scanning faster, right? So dt is smaller, like dV/dt, dq/dt, anything. The change of time is smaller. So I know that some of this is just mathematical, but the point is the current is dq/dt, right? And so if just statistically my change in time is smaller, that's in the denominator. And so I should just stop because this is just the mathematics. This is just math. I'm just answering your question with the thing you asked me not to do. But I don't know. I kind of like this explanation a little bit because it's like, if the change in time is smaller, this happens over a millisecond instead of 10 hours. dt is really small. So the amount of, even if it's the same Q, the same amount of charges pass, it's over a shorter period of time. And current is the change of charge over time. And so the time is shorter. It just makes this quantity larger. And so that manifests itself that way. The other way is related to diffusion changes. And so it's related to Fick's law. I also don't like this one because it just feels like it feels like almost circular logic or something. It's just weird. But again, I'll just sort of read this and try to talk through it. When the scan rate's large, it means that a potential is changing faster, right? Over time, over the same amount of time, I change the potential faster. So what that means is that the concentration gradient will be larger at the electrode surface. And you can if you look at Fick's laws of diffusion, this would track, I believe, if you look at the second law of diffusion, basically that the one of the effects will be that the concentration gradient is more dramatically changed as you change the potential faster. Okay, which is what Fick's second law relates. It relates the change in potential through time with the change of potential or the change of concentration, through time with the change of concentration through space, distance, right? And so the diffusion gradient will be bigger. And so because there's a bigger gradient, that just means there's more current that can pass. So it's like there's a it's like you're more dramatically, let's just say, drawing species to the surface over a shorter period of time. And if there's more stuff at the surface to react, the current will be higher. Something like that. And maybe you're like, I don't know what he just said, and I barely know what I just said, because I hate this. I struggle with
No,
it.
okay. So I think you're exactly right. This is how you get to the physical interpretation.
Mhm.
So I know we hate math and we don't want. Okay,
I
so
don't hate math. I just
we don't want to use a mathematical explanation.
Yeah, it's
for
tough.
understanding.
It's
okay.
tough.
So here's another way. This is literally building on exactly what you said.
Mhm.
The current is proportional to the amount of stuff near the electrode surface.
Yes.
Absolutely. It's
Yes.
concentration.
Correct.
How much stuff you have next to the electrode is going to determine how much current you get.
Yes.
And so we can we can think of this again, like the Butler-Volmer equation allows us to get a physical picture of this. So if you have the Butler-Volmer equation,
sure I do. Kinetics. Here it is.
yeah. So here we go. So this is Butler-Volmer. Now instead of exchange current density, pretend that it's like current or not current, concentration.
Yep.
Right. So when the scan rate is slow,
so this is like concentration.
Yeah. So you can think of it. Yeah.
Not IFC, but you can think of this as concentration. Whatever.
Yeah. Or there's concentration. Like I'd replace. The idea is that concentration is being multiplied by the exponential part.
Oh, I see.
Right.
Yeah.
So we have this concentration that's being multiplied by the exponential part. As you go at slow scan rates, that concentration has lots of time to change. It's got lots of time to change. It has a lot of time to go down. Right? If you're going faster, you're able to get the concentration. You know what? Hey, hold on 1 second. We have this really awesome software called Aftermath Live.
Amazing.
Right? So let me pull up. I'm gonna just pull up. I'm gonna use just Aftermath right now with simulation to make it, just to get it faster.
But I think the gist is that you change the potential so fast, the concentration's still big at the surface.
Yeah, and
you have a huge over potential, so now your current is going to be really high. Something like that.
Yes. Yeah. That's exactly right. So all right. So I'm showcasing our CV simulation stuff, and what I want you to pay attention to is and I'm going to make this a big number. Oh crap. Big number. All right. So what I want you to pay attention to is surface concentration as a function of time. Because this is the key here, is you always have this like 100% and like 0%, and it's always here. And so this always has to happen if and again, it's also again with the Butler-Volmer equation, if the kinetics are sufficiently fast, and I have a situation where the kinetics are sufficiently fast, the system becomes Nernstian. We are at a potential where the ratio of oxidized and reduced species must be a certain way. It's got to be 10 to 1, 100 to 1, 1,000 to 1. It's got to be that way if the kinetics are fast. When you reach a potential, this time element, right? If I keep changing this, like if I make this lower, it says this is like 20 milliseconds. If I simulate it, now it's 2 seconds. So and it is this, I know it's weird. I'm going back to like, well, it's math.
It's math.
It's math.
It's always math.
But this, looking at how this concentration versus time profile changes, because I have so much more material at the electrode surface in a shorter period of time, that it necessarily means the current has to, I made it way too. Actually, no, it's the same thing. I just have to rescale it. Oops, rescale it. It just like, it has to go from this low amount to this high amount, because kinetics demands that it's there. The potential and the Nernst equation and the kinetics demand that this process occurs. And when you think about electron transfer it's like femtoseconds time scale. It's so fast. So we don't even need to think about this. Milliseconds doesn't even matter. So if the kinetics are fast, and if I made the kinetics slow, then this stuff doesn't matter as much. But there's a combination of mathematics, as well as the physical argument of like, hey, if I had less stuff, which is to say I had this concentration at the electrode surface, which is this view, and if I go down to here at the beginning, if I have less of it, right? So it's only the concentration at the surface that matters. Here at this level, like this is 7 like millimolar or something, 0.7 millimolar. If I have this much at the surface, only this amount matters for the electron transfer. This is the only amount that's gonna help me get a maximum current from my system. This over here doesn't matter. This is gonna matter later. Yeah, it's just gonna matter later. So I think I only point this out to you because yes, there is this mathematical thing, but physically I've struggled with this as you know. It's like, because if I had chronoamperometry is another kind of good example of it, because you're stepping the potential, you're going instantaneously. Like that peak current is super high, way higher than in your cyclic voltammetry. And if you want to think a little bit more about this, I would recommend checking out Aftermath Live, which is our simulation software. You can, as well as check out. I have a video on chronoamperometry as well, but you can play with stepping the potential as if it was a bulk electrolysis experiment, to see like, hey, when I have this diffusion coefficient, this kinetic rate constant, this potential, and I set the potential, what's my peak current that I get? Then do a bunch of CVs at progressively faster scan rates, and it's like you'll like, and no capacitive effects. You'll almost never get to the peak current. It's almost like a limit, sort of say. Actually, I should try that. This is one thing that you can try as you're learning electrochemistry about why these things happen. So, Tamoga, I hope that was helpful. I hope that gives you a little bit of physical insight.
And the second part of his question was
square root of scan rate.
Yeah, why basically the Randall-Sevcik equation. So why is the proportionality for the square root of the scan rate? So the answer is also math. And there really isn't any other way to put this one, as far as I can tell. There might be some physical explanation for why things move in a certain way, but the reality is that this is the Randall-Sevcik equation, right? And it relates current to the square root of scan rate. And why is that? It's because, which I would have to learn and figure out myself. I won't do now. I don't know 100%, but basically the Randall-Sevcik equation, I believe, is somehow derivative of Fick's laws, or at least it comes in part somehow from Fick's laws. And the answer in some manner mathematically is that when you set up the assumptions of the Randall-Sevcik equation that lead to the Randall-Sevcik equation, and you solve whatever iteration or derivative of Fick's laws that you're using, you end up with a square root term. That's just what happens.
Yeah, it's
something like that.
Yeah, it's kind of. I have found that when somebody asks, why does something, physically, why does something triple? Like I can't answer. It's like I can't answer like a math response without another math response.
Yeah.
But I will say this, which hopefully, Timon, you'll find this useful, is that things that are diffusion controlled processes have a 1 over the square root of scan rate. 1 over the square root of time dependence. So you observe. So with the square root of scan rate, it's like voltage over time. You have 1 over square root of time.
Yeah.
In the Cottrell equation, you also have a 1 over the square root of time. In a rotating disk experiment, you have square root of rotation rate. That's rotations per minute, per time. So everything that is a diffusion controlled process ends up having a 1 over the square root of time dependence. And so whether it's cyclic voltammetry, where it's the square root of the scan rate, or Cottrell equation, where it's directly 1 over the square root of time, diffusion is the thing that gives you that square root dependence that you end up observing. And the physics about like, well, why does diffusion do that is something that I can't tell you more
That's
about.
that's why it's always a hard one. It's like, just like you said, like there's an observable phenomenon and a measurable one by mathematics of first principles that dictates basically that like current adjusts by the square root of 1 over the square root of time. It just does. It happens, right? And so like you said, the chronoamperometry, we have a direct just I is equal to 1 over the square root of time times a whole bunch of crap. And the peak occurs because of mass transport. I mean, it's kinetics and mass transport, interplay, but basically like the peak is largely a result of mass transport, which means you'll have a 1 over square root of time, and scan rate has 1 over time. So like it all tracks, it all makes sense. But trying to explain, and it's a good question, Timogna, like I think about this stuff all the time. But trying to explain like, well, why, like physically, do molecules move with a 1 over square root of time dependence? It's kind of like asking, well, Ohm's law says V is equal to IR. Why is it not why is V not equal to 2 IR?
Why is it
It's
linear?
like, I don't know, because we just measure voltage and current and they happen to be proportional. And there's no 2 in there, and there's no 1/2 in there, and there's no exponent. That's just what happens. It's like, again, you could probably like do some like quantum answer. There might be like, well, electrons move this way, and I don't know, like there might be some eventually answer, but the reality to a certain extent is that like sometimes we just observe stuff and then the math, that's it. Like math is the answer.
And sometimes like we can kind of, unfortunately it is one of those weird like math is the answer, because I'm even thinking about like what else in life has a square root dependence. Like we can talk about exponential growth, compound interest and all that stuff, and you can see, it adds on top of each other, and then that adds on top of itself, and on top itself. And how do you there
must be some.
Well, then how do you inverse that to square root it, and then associate that with a physical process?
I was gonna say like half-life decay. That's not square root.
That's
a whole different thing.
But
anyway, there must be. But you're right. It's kind of somewhat unique for electrochemistry. This kind of repeated, relationship.
But Timogna, I'll say, oh, well, he also asked a question about like, okay, proportional to the scan rate for a surface absorbed species. Okay, I don't. Well, okay, so here's one thing to at least keep in mind is that capacitors also have a linear relationship with scan rate. The current associated with charging a capacitor, Q is equal to V times T, and then, capacitance times V, and then the current for a capacitor is equal to the capacitance times the scan rate. It's a linear thing. It's also a surface bound thing. So naturally, you can almost think, okay, all surface bound things, because of their proximity, have a linear relationship. And perhaps that's because it's very fast for those things to form. Actually, you know what? Maybe that's the physical.
It's a speed thing.
It's a speed thing, but it's also this also gives us a better understanding for the physical interpretation of this, because with diffusion you have a rapidly decreasing concentration gradient that curves, because like you're always losing stuff as it hits, and it just keeps going down. It just keeps going down and keeps going down, and that is and that's similar to the square root. But when you have something that's just like, I have everything all at once, and then once it changes, I change directly, then it becomes linear all of a sudden. And that's mathematically how we describe it, because we have more, or we have less, or we have direct and we have indirect. So all right.
The speed thing works too, just from a simple fact that speed is time.
Yeah.
Like ultimately the answer is all, I think, time. Like everything is in time, and how rapid or not rapid something happens. And then ultimately the answer always returns to, and then we apply math to the time, and it's math, and it's no, but I love this question.
Yeah, it's a very good question.
I love, because
me too.
Like I do all these webinars I do and everything. Like I am obsessed with trying to explain things in clear words.
Yeah.
That's not like, well, if you just look at this equation, this is why things happen. It's like, no. Why they happen is because, can I explain it?
Yeah.
In reality. Like that's why I drew a capacitor with a bumpy surface. Like that's a thing you can think. Like maybe it's correct, maybe it's not perfectly correct in all cases, but it's like I'm trying to explain it rather than just like, well, because if you make this exponent
Yeah.
0.75, it works.
Yeah.
I was like, well, what does that even mean? I very much crave those answers too. So anyway, I appreciate your questions.
Yes.
That's all I kind of want to say. We're hitting close to our time.
Yes.
What do we want to do?
Yeah, I would say there was a person who spammed the chat, and if you watch the beginning of the webinar, or of the live stream, you cannot spam the chat. I will ban you. I will say generally, RJ Gamer did say, is it possible? Got a dry cell?
I don't know what that means.
Oh, I think he's talking about like no liquid electrolyte.
Oh,
maybe there are solid electrolytes and stuff like that.
It's possible.
So it is possible.
You can do. I mean, generally speaking, I guess without getting into a million details, because there's probably a lot of follow-ups that you could do here. But generally speaking, of course, it's certainly possible to do electrochemistry without liquid. It is possible.
Yeah.
It sometimes presents its own other subsets of problems, and it can be tricky. But generally, I would say, yeah. Ahmed has a couple of questions on batteries. I can try to talk about this, and this will be the last. I think try to not leave you hanging here. Also, just pre-dish your business student, but this is interesting.
Yeah, I'm glad you.
If you think this is interesting, it means you have a problem with your brain. Welcome to the club. We're electrochemists. We all have a problem with our brain. And
everybody say hi to Pradesh.
That's right. Hi. Welcome. We're all friends here.
Yeah.
We're all supportive of each other's mental instability because we're doing electrochemistry.
Yes.
But I appreciate you being here very much. Ahmed has a question. Has a couple of questions here. I'll try to talk through this relatively quickly because we are at about our time limit here. It says, can you please explain the physical meaning of the NP ratio for coin cells? So I just had to remind myself, the NP ratio is like the ratio of how much anode and cathode stuff you have, basically. I guess I can say a couple things about this. One is that as a general rule, when it comes to like a full battery, a full anode cathode, battery, your job as much as possible is to match everything as close as you can. Now there's exceptions for like when you have like a half cell with lithium. I know that's like your next question and everything. But the point is, if you have like, it's why your capacity, so like capacities, you're trying to match capacities and match mass of anode and cathode so that you have like lithium is being passed between anode and cathode during charging and discharging. That's what it's doing. And so when you're charging a lithium ion battery, lithium ions are being passed from the cathode to the anode. And when you're discharging, the anode is passing them back to the cathode. Now, because of that fact, if you have more lithium than can be passed or not enough lithium to pass on one side or the other, you might have a problem, right? For a number of reasons. You can have plating, you can have dendrites can occur. You might over-oxidize, over-reduce one side if it's like expecting more lithium, but you don't have it. You might have extra lithium that can plate, cause a problem. You might oxidize or reduce your anode or your cathode itself. The SEI can break down. There's a lot of like subset of problems that can occur. And so in some sense, like the NP ratio for like a perfect set of anode, cathode, or whatever, you're trying to match that. And so that's one of the reasons, for instance, in a typical cell, something like a cathode material like LCO or NMC or something like this, usually the theoretical capacities of cathode materials are like 150, 170 milliamp hours per gram. The capacity for carbon is like 370 milliamp hours per gram. So let's just say it's like 2x. It's not exactly, it's close to that or whatever. But like the per unit of mass, the anode typically has, let's just say, twice the amount of capacity, which means twice the amount of lithium that it can store in and out. Okay. So what that means is that on average, the cathode, you need twice as much mass. And assuming everything has the same density, which it doesn't, but let's just assume, it means your cathode has to be twice as thick. So this is what we mean sometimes by the matching of the anode and the cathode is like, well, if I have the same thickness, the same mass of my anode and cathode, well, my anode can take way more lithium than the cathode can provide. So I'm kind of not in a good place here. I have way too much extra capacity on my anode side. It's like if it tries if it has all the lithium in it and it tries passing it to the cathode, it's like, oh, my cathode, I can't take anymore. I'm full, right? I can only take 170. You're giving me 370. I don't have any room for it. Or the cathode's passing it to the anode and it's like, hey, come on, I can take more. It's like you're handing someone groceries and you give them one bag, but they have 2 arms. And it's like, well, I can take another bag. Give me another bag. And you're like, I don't have any bags to give you. And you're like, but what's my arm going to do? Do nothing? That's ridiculous. I need a bag of groceries. The anode is sitting there with no bag of groceries. What's it supposed to do? It's miserable. It needs more groceries. Give it more groceries. Do you want to take 15 trips to get your groceries in the house? No, you want to do it in one trip, like everybody. If you're on the 8th floor of your apartment building, you're carrying 57 bags at once. So you don't have to take the elevator or the stairs twice. That might have been more information than you needed. But that's what
very real.
That's what I used to.
Real talk.
I lived in the 4th floor once, and it was like every time I went to the grocery store, I was like, I don't even care if I bought a rhinoceros at the I'm carrying this up in one take. I refuse to go back downstairs.
Yes.
But this is what you're doing, matching the anode and the cathode. You're trying to make sure that roughly as much as you can, what's being passed back and forth is like matched, so you don't have that problem. Now, the NP ratio can make more of a difference when it comes to things like plating and whatnot. So like, you can see a little bit of stuff. Just trying to remind myself, but like, if you have a half cell, and this is sort of, again, the last thing I'll talk about for just a couple of minutes here, the difference between the full cell and the half cell for a lithium NCM coin cell. Well, whether it's a lithium NCM or it's anything else in particular here, the matching is less critical for half cell studies. And to that point, you wouldn't make that's why it's called a half cell. Like if you're using lithium metal as one of the electrodes, like the anode or the cathode, right? The lithium is like an infinite source of lithium. So it's like, it's handing you grocery bags over and over again. And you're like, all right, I only have 16 arms, cause I'm like a monster. Well, now it's giving you a 17th grocery bag and you're like, well, I don't have any arms. And it's like, well, I have more lithium to give you. I have more grocery bags. It's just going to it's going to be look, as many arms as you have, then I will give you grocery bags. That's it. It has more to give. And then when you're coming back and you're like, well, I'm going to return these groceries because it's not what I wanted. And you're giving them back. It's like, I can take as many grocery bags as you want. It's got infinite ability to take and give lithium metal. And so what that means is that it's not going to limit you. Back to the science of it and forget groceries. Is that when you're using a lithium metal as the other electrode with whatever you're studying, anode or cathode, it is like a perfect other electrode. It can take lithium, it can give lithium infinitely. So it's not the limiting factor, so to speak. So that whatever you're studying on your other side will be the one that limits fundamentally, right? Now there's safety problems that can occur over long periods of time. If you were to try to like make a real battery with just lithium metal, there's a reason why it's not used. And there's safety issues. It plates, it forms dendrites. There's all kinds of other problems. But the main difference, generally speaking, between the full cell concept and the half cell is that the half cell is being used to like really study the independent characteristics of just the anode or the cathode, because you kind of like sometimes perhaps not and shouldn't, let's just say, but generally speaking, you ignore the lithium metal for the most part, because you just assume it's the ideal other electrode. And so you're really like studying just the NCM or whatever else that you're studying. And NCM is a cathode, I think. Yeah, nickel, manganese, cobalt. Yeah, for some reason I'm blanking on it. Yeah. So you're studying just the cathode behavior. So you would basically look at that behavior of your NCM lithium and say, well, lithium's the anode. It's like perfect. I'm ignoring it. If you make a full cell with graphite, for example, in NCM, you're studying all of it. Like, it can be tricky sometimes. This is another, you might take impedance, you might do charge discharge. It's like, well, is it the NCM or is it the graphite that caused this problem or made it great? It's like not always clear, right? But there's a reason you're studying a full battery. You're trying to see how it works, all this kind of stuff, right? Whereas with a half cell, it's like you're trying to develop a new material. You're trying to see if this material will work. You're trying to see if this loading will work, if this recipe with this amount of binder, this amount of carbon, all this stuff. That's what you would use a half cell for, to take the other electrode out of the equation. It's like ideal, it's perfect, so to speak, whatever, for some investigation, and you can just focus on the one electrode to see how it performs, and then you can compare. Because if you make a bunch of full cells, it also, you can compare how they operate. But it's tricky if, like, well, what the other electrode is maybe contributing. Whereas with the lithium half cell, you can take that other electrode mostly out of the equation and say, it's ideal. Now I'm just studying the electrode of interest. So I hope that kind of clarifies that a little bit for you. And I know we have another bit of a thing here, but I think we're kind of out of time. So.
Yeah, we are out of time. Yeah, I don't know. I mean, this person's like,
hopefully you see. Did you link our?
I linked the YouTube video. I also linked, but I think I just linked the basic YouTube video. But he sounds like he needs like some help with, like, I don't know, understand. But I can tell you something very, very quickly about G. So your question about, like, why in CV is it called negative scan when you say you don't understand what you would look for, especially if you had like some kind of unknown analyte. Totally normal. So typically, if you have an unknown analyte and you're doing something for the first time, it's okay that, like, you're not going to get things right the first time. So you may do some what we call exploratory CV. And what you would do is you would just scan in like a relatively broad range with and without the analyte, and then look for the differences. And it doesn't matter if you're going positive to negative, negative to positive, what have you. By just doing a bunch of those experiments, you'll start to notice, like, oh, my current is 0, or oh, my current started at minus 100 or something. You'll start to learn some information, and you're really looking for differences at that point. So pick a big voltage range, like just start off with plus minus 1 volt. And then with your unknown analyte, scan it. And then if you don't see anything, any differences, increase the window a little bit, the range, and then see if you pick it up or detect it. But it sounds more like, because we're out of time, I can't give you a more thorough answer. But you do need to, it sounds like you need to just play around with it in the lab first. You need to get your hands dirty a little bit.
We made it 2 hours and 10 minutes.
Yeah.
And you still couldn't escape a question on potential window.
Well, yeah. I mean, I didn't talk about how to get, the potential window. I just said, just pick one, two.
This is your cross to bear.
It's okay.
You will talk about the potential window every Friday for the rest of your life.
That's okay. I'm okay with that.
You will be on your deathbed at hopefully a very old age.
Yes.
And it will be Friday, and I will walk in.
Yeah.
or wheel in, depending on my health as well.
Yeah.
Because I will also be very old.
Yeah.
And I will say, Alex, I know that your brain is mostly gone, but it's time to talk about the potential window. And I will talk about Lugan capillaries, and we will commiserate.
We will commiserate.
That will be our life.
Just tell the AI to do it.
AI can't do it like you do. I remember back in the day.
Yes. We have just use our stuff.
Yes.
Our equipment. I got Frank to program this algorithm for us to do it for you. My last wish.
My last will and testament. Oh man.
Yeah. Abijoy. Next week. I think next week.
Yeah,
Halloween. We'll be here.
That's right. It will be spookier than ever.
Yeah. Come back to the live stream. We start 1 p.m. Eastern Standard Time. You can even ask your question ahead of time. We could, and give us some details on what you're trying to do, and then we can then spend more time. Just because we only do this for 2 hours and we're out of time. We're way over time.
That's right. So. We are over time, so we're about to call it here.
Yes.
So thank you, everybody, and thank you for the questions. Like Alex said, we should be here next week on Halloween Day. Ooh, maybe I'll be wearing a costume.
Yeah.
Actually, I probably will. I know what I'm going to wear.
I won't be wearing a costume.
gonna-
Frank doesn't like it when we wear costumes.
Oh, I don't care. I'm wearing something fun. I know what I'm going to wear. It's going to be great. You'll have to wait till next week to find out.
Yeah, that's right.
And until then, I hope everybody has a spooky week. We'll see you next week. Bye.
Bye.